Let's take an in-depth look at catalysts so that you can explain catalysis in terms of the physical effects, the thermodynamics, and a little bit about reaction geometry and mechanism. And then in part 2, we'll give examples from biochemistry. The catalyst is a substance that alters the speed of a chemical reaction. It participates in the reaction without undergoing permanent chemical change itself. As the reaction goes on, there's a change, but at the end, everything is as it was, except the reactants have become products. Now, catalysts can either speed up a chemical reaction or slow it down. Now, physiological reactions, as we'll see in part 2, always involve catalysts and catalysis. Industrial processes frequently do. Let's recall, if you perhaps have seen the decomposition of the white salt potassium chlorate, it produces oxygen and potassium chloride. If you mix in the black powder manganese dioxide, that will speed up the oxygen production. And then you can recover the manganese dioxide by dissolving or slurrying up all the product with the manganese dioxide and filtering the manganese dioxide out. Catalysts, therefore, can be reused, perhaps after some reprocessing. Now, homogeneous catalysis refers to using a catalyst that's in the same phase or state as the reactants. The manganese dioxide is a black solid, potassium chlorate is a white solid, and so that is homogeneous. If you take hydrogen peroxide and heat it up, it will eventually turn into water and oxygen. You can add manganese dioxide to it, but since it's a solid, that's a heterogeneous catalysis. We can try the bromide ion in a 1 molar potassium bromide solution, mixing that with the hydrogen peroxide. This reaction is one of the rare ones in which we can actually see the formation of an intermediate step. The hydrogen peroxide reacts in the first step with bromide and the presence of hydrogen ions to form bromine, kind of a solution of bromine, and water. The bromine then reacts with additional hydrogen peroxide to recover the 2 bromide moles and some hydrogen ions, and the oxygen gas is produced. Overall, the bromide and bromine disappear and we're left with the initial reaction. The bromide then participated but is not permanently changed. Can the catalyst be changed in a chemical reaction? Well, clearly the answer is yes, but the original chemical identity has to be recovered by the end of a reaction, or else we don't have a catalyst effect. In this case, the bromide is changed by the peroxide, but it's temporary, and as long as there's adequate peroxide, the bromine that is produced in the intermediate step will be converted back to bromide. Now, how is it that catalysts operate? What are the thermodynamics of the process? Well, we look at the Arrhenius equation. A constant is equal to A times the exponential e to the negative e sub a divided by RT. A is the frequency factor. It relates to the number of favorable collisions per second and therefore the collision geometry. E sub a is the activation energy, and of course R is the gas law constant and T the absolute temperature. Catalysts can alter either the A factor or the E sub a, but altering E sub a, as you see, since it's in the exponent, will give you the most dramatic effects. How do catalysts lower the activation energy then? Well, generally they provide a new reaction pathway or mechanism. For example, each of the reactions between the hydrogen peroxide and bromide or bromine must have a lower activation energy than the uncatalyzed decomposition, or they wouldn't happen at all. Here is a reaction profile. Here are the reactants. Here's the products of the hydrogen peroxide decomposition. Without a catalyst, the activation energy is fairly large. But with the catalyst, with the bromide and hydrogen ions present, we have an alternate reaction pathway. The mechanism is lowering the activation energy overall to incorporate these two steps. And the intermediate state of the catalyst is elemental bromine. Homogeneous catalysts have a definite advantage, and the kinetic molecular movement within the single phase automatically brings together the molecules of reactants and catalyst. It's random, but it's predictable. The contact happens without doing anything else. You don't have to, for instance, grind up a powder more finely. It's already as fine as it can be. Now, heterogeneous catalysts exist in a phase different from that of the reactant molecules. And most of the time, catalysts are solids reacting with gaseous reactants, or solids reacting with liquid reactants. Why is this? Well, many reactions are facilitated by taking place on the surface of a solid. So the reactant then goes to the surface of the solid, and this is particularly true if there are available d orbitals in the catalyst. For example, we can electrolyze water, acidic water, and we use platinum electrodes, and platinum focuses on not just supplying the electrons or taking the positive charge away, but it also provides a place for the reaction to occur. Hydrogen occludes or dissolves in the surface of the platinum. This makes the electrolysis reaction complete more quickly. Now, reactant molecules, as with the product, hydrogen, in the electrolysis of water, reactant molecules adsorb on the solid surface. That means they actually dissolve in the solid surface. That makes the surface atoms or ions reactive. It creates an unbalanced valence situation, and then unused bonding capacities in the catalyst will attract the electrons. So you can imagine half-filled or completely filled d orbitals available on the surface of the catalyst, and the electrons in the reactant are attracted to them. Now, impurities may also occupy the surface reaction sites. Places where reactants are attracted, you may already know from biology, are called the active sites of the catalyst. You can increase the active sites by treating the catalyst. For instance, in some situations we can treat it with active steam, and it makes little pits in the catalyst, giving it a higher surface area. Or we can bond the catalyst, particles of the catalyst, to a porous ceramic, and that gives it again more surface area contact with the reactants. We'll give you an example. Ethene reacts with hydrogen gas to form ethane. It has a fairly generous exothermic character, negative 137 kilojoules, but it has a very high activation energy. If you add powdered nickel, palladium, or platinum, the reaction proceeds briskly even at room temperature. What's happening is at the surface of the, for instance, platinum metal, hydrogen is breaking down into two hydrogen atoms. And you notice that little unshared electron. And they swim through the metal surface and lodge in the pi orbitals of the next ethene molecule. So the pi orbital then is converted into a sigma bonding orbital, bringing the carbon together with one of the hydrogen atoms, giving us C2H5. And again, this is highly reactive, and the next hydrogen atom that swims past will react with that unshared electron off of the second carbon, and that'll yield the C2H6. Here's the experimental apparatus for the hydrogenation of ethene, and you'll notice the platinum or palladium catalyst in the reaction chamber, and that'll of course have a high surface area. Now the hydrogen-hydrogen sigma bond in the hydrogen molecule breaks, that's endothermic. The carbon-to-carbon pi bond breaks under the influence of the catalyst, that's also endothermic. Bond breaking is endothermic. These make up the activation energy. The catalyst then provides the reduction energy needed to break the hydrogen-hydrogen sigma bond so that the energy-releasing reaction making the carbon-hydrogen sigma bond is easier to get to. There are some important industrial applications beyond that hydrogenation. Precious metal catalysts, base metal catalysts, or metallic oxide catalysts are used. We'll talk precious metal first. Rhodium often works at lower pressure with exceptionally high selectivity. Gives us a low pressure reduction of aromatic rings like benzene and naphthalene. It also helps with the reduction of aldehydes and ketones, and aromatics, ketones, acids, and vinylic olefins. Precious metal catalysts like palladium, catalysts, the most widely used family of precious metal catalysts are in the palladium-platinum family. Carbonylation is one. Dehalogenation, taking away chlorine or bromine from a molecule, organic molecule, and the amination of alcohols and aldehydes to put the nitrogen onto those compounds. Base metal catalysts are also used. Copper is used to dehydrogenate butane to 1,3-butadiene, very important in organic synthesis. It can also dehydrogenate propane to propylene. The Houdry process produced high-octane gasoline back in the 1920s and 30s from coal. Metal oxide catalysts are often used. Titanium dioxide is called the Claus catalyst, and sulfur recovery units are gotten from there. It's designed for simultaneous conversion of hydrogen sulfide, sulfur dioxide, and two others that come out of, for instance, coal burning plants. And that is our end of our part 1. In part 2, we will talk about the biochemistry and biological catalysis.